Okay. All right, let's start. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor to host Molei Tao, who is an associate professor in Georgia Tech. He received the bachelor's degree in mathematics and physics in 2006 from Tsinghua University in China, and the PhD in control and dynamical systems with a minor in physics in 2011 from Caltech. Afterwards, he worked as a postdoctoral researcher in computing and mathematical science at Caltech from 2011 to 2012, and then as a current instructor at the New York University from 2012 to 2014. From 2014 on, he has been working as an assistant and an associate professor in School of Mathematics at Georgia Tech. He is a recipient of the W.P. Carey PhD Prize in Applied Mathematics in 2011, American Control Conference Best Student Paper finalist in 2013, the NSF Career Award in 2019, and ASTAT Best Paper Award in 2020, IEEE Best Student Paper Finalist in 2021, and Colin Peck Scholar Award in 2022. Today, Molei will talk about trustworthy learning of mechanical systems and Stiefel optimizations with application to transformer and optimal transport, which is a very interesting topic. So please enjoy it. And now, without further ado, let me pass the baton to Molei by asking one random question as usual. Today's random question is, what is your favorite things to do other than research? Molei, you can answer that and then continue your talk.
Thank you very much for the very generous introduction. So I recently started twittering because I was told that if you work on machine learning, you have to Twitter, otherwise nobody knows your research.
Oh, really?
And I thought, well, that's a joke. But I never, I mean, I'm not a very social person, so I never used these. And I only have like, under 100 followers on Twitter. So I guess, it doesn't really matter. But I write on my Twitter that I'm actually a former semi-professional gamer. So I wish I still could have time to play games.
Okay,
But no.
That sounds fun. Okay, thank you, Molei. Stage is yours.
Yeah, but anyway, yeah, thank you so much again. It's a great opportunity for me. I'm really happy to be here and give this talk. So I thank the organizer, Dr. Tree, for his kind invitation. So so my talk has a very long title. It doesn't really matter, as I'll explain. So the key message that I want to convey is that there are a lot of interesting interactions between machine learning and dynamics that can be explored. So for example, so if you go from the left to the right direction, you can use machine learning to solve dynamical problems in science and engineering. If you go in the other direction, you can actually use dynamics to design and analyze optimization, sampling, deep learning algorithms, for example, for machine learning. So of course, all these are very vague and broad. So what I'll focus on is actually geometrically structured dynamics in this talk. And in particular, in part one, I'll try to learn structured dynamics from data and use what is learned to make predictions of the system. And I want to do actually very long time prediction. And as you will see, the inference of the structure is very important as it allows us to actually have accuracy in a long-time prediction. For the second part, I'll focus on optimization. I'll optimize actually functions that are defined on manifolds using actually acceleration from momentum. And the work, as you will see, will be actually via structure preserving dynamics in both continuous and discrete time. I know that I mentioned other buzzwords, such as sampling or deep learning. I will not talk about them today. But these are some of the things that we're actually very interested in. For example, sampling is something that we interpret in a broad sense, including optimal transport, generative modeling, etc. So if any of you are willing to talk to me after the talk, I'll be very excited. And similarly for deep learning, so we believe that dynamics can actually help us gain a lot of good quantitative understandings of deep learning and even help improve deep learning. So I will be very excited to chat more. But let me directly jump into my first part, which is well. So this sounds very scary, but really I'm just going to be focusing on a special instance in which you use machine learning to actually understand dynamics in sciences and computing. So in particular, it'll be based on a joint work with my former student, Yanyi Chen, which is on learning mechanical dynamics from data. And you can find this work published in a machine learning conference, ICML. It's available online. But let me first explain why do I want to predict the dynamics of mechanical systems. It's because our world is actually mechanical. For example, here is a planet that is actually precessing around a star. And imagine you are Kepler or Newton. So at your time, you didn't really know the underlying governing equation that generates the continuous trajectory. All you have are actually those red dots, which correspond to observations of the system at discrete time points. And what you want to do is you want to understand the underlying governing equation, the underlying governing physical law, and also make predictions such as the ones given by the green dots. Okay, so this is really a long time prediction. It sounds very difficult, and it is, but it's not impossible, because even though you don't know the underlying dynamics, you have some knowledge. You know this is a mechanical system. It has structures. For instance, oftentimes you have conservation of energy, of linear momentum, angular momentum, etc. And if you dig deeper, there's actually an underlying geometric notion called symplecticity that is preserved by the dynamics. So what we want to do is we actually want to build, we want to hardwire this conservation of symplecticity in our learning model. And as a consequence, as I will show, we can actually obtain superior prediction accuracy because of that. So so the setup is the standard one. So we have training data, which are multiple time series. I is the index for discrete time. J indicates which sequence it is. And what we assume is that there is some latent dynamics generated by a map phi. So this phi is like an evolution map. It evolves the state at time I to time I plus 1. And the goal, therefore, is very simple. We just want to learn the evolution map from the data. And then the task of forecast is trivial. You just have to iterate this map many times. And I want to emphasize that sometimes you want to actually iterate really a lot of times, and that's what I meant by long time prediction. That sounds very natural, but in fact, that's not what people do the most in the literature. So traditional approaches are more based on differential equations. So, so what is often assumed is that there is an underlying latent dynamics that evolves in continuous time that generates a continuous trajectory capital X. And then what you see, the data, is really snapshot. Well, the data are snapshots of the continuous trajectory at discrete time points. And the goal there is to learn the vector field F. But if you think about it, f is different from phi, okay, unless the time interval between the data points is infinitesimal. But of course, in reality, this is rarely the case. If you try to analyze this vector field-based approach, there are several sources of inaccuracies. Number one, okay, you are given really the discrete time data, so you have to use them to approximate the time derivative. That's numerical differentiation error. And then you have function approximation error because you want to actually find the f that matches the time derivative. So you have function approximation error. And then once you have found the differential equation, you have to integrate it numerically to get the future prediction. So you have numerical integration error. If you use the map-based approach, you only have function approximation error. So you still have error in approximating phi, but that's it. In addition, you can hardwire physics into the learning model. And what do I mean by physics? So in this particular case, I mean symplecticity. So I require this map. By the way, this is symplecticity in coordinates. So I require this map to have a Jacobian that satisfies this quadratic equation for all spatial points. Okay, why do I want this odd condition? It's actually very intrinsic. It's basically like a signature of mechanical systems. For example, if there is a latent dynamics that is Hamiltonian, then no matter what the Hamiltonian is, the solution flow phi is always going to be a symplectic map. Okay, so that's why we actually want this badly. We want this to be a hard constraint. We want it to be satisfied exactly. We don't want any approximation in this. So things like regularizers, etc., are not considered. So therefore, our goal is to find a map phi that matches the training data while satisfying this constraint exactly. That's actually pretty challenging. So that's why we actually use fancy mathematical tool to do it. So so there is actually a deep theory that says, roughly speaking, there is a one-to-one correspondence between a symplectic map and something called a generating function. So what do I mean by that? Okay, so a symplectic map evolves the current position and momentum to the future position and momentum. A generating function, on the other hand, is different. It actually depends on a mixture of present and future. For instance, here is an example where S depends on the current position and the future momentum. And then you have to have equations that link all the four variables together. So in fact, there is a system of PDEs that this generating function has to satisfy. So basically, all the current position Q and P and the future position Q and momentum P are matched through this PDE. So I don't think I have time to go into the profound theory of Hamilton-Jacobi, which is behind this. But at least in terms of what we can do, it's very clear. Now we can just find a neural network to parameterize this function S instead of this evolution map phi in order to match the training data. And therefore, we call our resulting method to be generating function neural network. To be a little more precise, you can use your favorite neural network. Yes, so symplecticity has good effects that I'll actually explain in a moment. So I'm answering a question that was typed in the chat. Basically, by gaining symplecticity, by ensuring exact symplecticity, I can get superior long-time performance, superior long-time accuracy of my prediction. So that's a great question. Thank you so much. You will see a quantitative version very soon. So coming back to the formulation, so you can use any of your favorite neural network, feedforward, ResNet, or anything fancier to parameterize this S function. So there's an underlying S function. You don't know what it is, so you're looking for an approximation to it. You use a neural network to do it, and then you require your neural network to nearly satisfy these PDEs. So you can therefore come up with an objective function which is the residual of the equations, and then minimize the parameterization of the neural network. Okay, so that's what you do for the training, and then you never have to worry about symplecticity. Depending on the neural network, your S may be your S theta may be a very good approximation of S. It could be a very bad approximation if you use a very small neural network. Bad architecture, you don't train it. Yes, the idea is not limited to neural network at all. So anything that can give you good function approximation will work. But my point is that you don't have to worry about symplecticity at all. So you can get a very lousy approximation of S, but you still get an exactly symplectic map. Okay, so because we are using a map-based approach, and also we have exact symplecticity, we can actually use some of the fancy tools from dynamical system called KAM theory. We can actually construct some theoretical framework which enables us to prove under reasonable conditions that you have a bound of the prediction error. So in this bound, these two are the predictions. So n is a number of steps of prediction, and these two are actually the truth. So you don't really know them, but you know they exist. They exist because there's an underlying latent dynamics. What is this epsilon in the error bound? So it's something that can be made arbitrarily small. It's basically the function approximation error of your neural network. So neural networks are universal function approximators. So theoretically, you can make this arbitrarily small if you try hard enough. The arguably most important part of this result is this one. So n is a number of predictions, prediction steps. H is the time step. So n times h is actually the physical time of prediction. And n here can actually go very big. And you see that the prediction time actually appears as a linear term inside the bound. So this is saying that the long time prediction error is actually linearly growing with the prediction time. This is pretty non-trivial because if you compare it to traditional approaches, the long time prediction error can be actually exponentially growing. And this is not because you have a bad bound. This exponential error can actually be attained. And this is really the consequence of having exact symplecticity. So I don't have the capability of talking about the KAM part of the which is theoretically non-trivial. But you need exact symplecticity in order to have linear growth. And that's why when we try the method on, for example, the prediction of planet orbits, our method has error that are at the very bottom when compared to some of the other popular approaches available. Here is another example where I try to learn something called the standard map, which is actually a mechanical system that is chaotic. If you haven't heard of it before, it doesn't matter. The key point is that it's a chaotic system, and it can be visualized by something called Poincaré map, which is the one shown here. I don't know if my cursor can be seen, but so basically here you have those white regions which are called stable islands, and they are separated by chaotic seas. And you want to capture the structures of those stable islands. And our method, namely GFNN, is the only one that can capture the major stable islands. But of course, it's not perfect either. So there are still a lot of things that can be done in the future. But still, it has better performance than other approaches. So that's why our method possibly has good applicabilities even to chaotic systems as well. So let me quickly summarize. By using a map-based approach, we can actually involve the tool of generating function and develop a generating function neural network. that gives you exact symplecticity of the prediction. And because we have a map-based approach, exact symplecticity, and also generating function, we actually managed to revamp the classical KAM theory to develop a theory of KAM type for generating function. And this theory allows us to actually prove superior long-time performance, superior long-time prediction accuracy of our method. And that's why we say the method is trustworthy, because we know we have actually an error bound, which is pretty good. Okay, so I'd like to pause for a second because this finishes my first part. If there's anything that I can clarify, please don't hesitate.
There's a question in chat room from Thailand.
Oh, okay.
Actually, I had the same questions. He asked
Yeah.
in previous slides, is the simplicity, symplectic, simplicity minimization exactly, and symplecticity, the minimization exactly enforced if the minimization does not reach the minimum. For example, it's not 0, then it will not be exactly symplectic, right? I mean, the previous one, not this one. Previous.
You mean the other work?
There's the minimization
Yes.
slide. Yeah, that one, the bottom.
Right. So it doesn't matter what the value of this objective function is. So even if you don't train, as long as you use generating function, you give me any s, there is a corresponding symplectic map, and this map gives the evolution. So you always have symplecticity.
Yeah, but the thing is, S should satisfy that right-hand side, that ODE
Yes.
or PDE.
Yes.
If that PDE is not exactly satisfied if this minimization does not reach 0, right?
Okay, I see. So yeah, so for example, if you think your data comes from a mechanical system, but it doesn't, then yes, this will not reach 0. But I would there is not much I can do. I think it's more like a modeling issue rather than a methodology issue. So
yeah, so if it does not reach 0, then S is not exactly satisfying that PDE or ODE. Therefore, the symplectic map phi
no,
that doesn't
I see. Thanks for the great question. But S doesn't satisfy the PDE for the data, but S actually generates something else. So S has a corresponding phi, and the trajectory generated by phi will be exactly satisfying the PDE. So S will give a different prediction from the data. So that's for sure. But that still corresponds to the evolution of a symplectic map. It's just that if you're not trying very hard to match the data, you will not match the data.
Okay, so there's another question from Pat. He asked, what is KAM again? Just a high level summary.
Yeah. Thank you. Sorry, I was trying to rush through things. KAMs is the initial of 3 great mathematicians, Kolmogorov, Arnold, and Moser. So it's basically a theory that says that, okay, so if you have some mechanical system that is good, if you perturb the system a little bit, what will happen to your evolution after a very long time? Roughly speaking, that's what KAM theory is about. So in this case, you can see why it is being used, because you have some underlying mechanical system, and then as you predict it, you make errors at each step, and you want to know your prediction, which is another mechanical system due to symplecticity. You want to know how this new system actually evolves, how far it will deviate from the original, the latent mechanical system. So that's why KM theory is a major key in doing the error proof.
Great. Another question is from Faye. Are there similar long-term stability guarantees for first-order systems?
Okay, thank you. Yeah, I'm so glad to hear from so many experts. So, so it depends on what kind of first-order systems one can have. There is something called reversible system that has a similar long-time error analysis. I think it really depends on the structure. But of course, there are also systems in which things will, linear growth of error will not happen. For example, you can write fluid as first order systems, but you can even develop shock in finite time. So if you perturb the system a little bit, you get very different behavior. You can have also chaotic dynamics in which one perturbation will get exponentially amplified along with time. It's complicated, but there you may not necessarily look at accuracy of a single trajectory, but the statistics of a lot of trajectories. So then you have to do something else. I hope I'm answering all those questions, but which I found to be all very great ones.
I think it's good enough for now. I guess you can move on,
Okay.
Molei.
Okay, thank you. Thank you all. Okay, so let me go to the second part. So in the second part, I want to do the other direction, which is to use structured dynamics to design machine learning algorithms. And in particular, I'll talk about a joint work with my student Lin-Kai Kong, Yuqing Wang, and the work was very recent. It's basically on how to optimize a function defined on a manifold called Stiefel manifold in a very fast fashion. So that's what this word momentum is about. You will see momentum basically helps accelerating the optimization. If you have by any chance heard me talking about Lie group optimization in the past, it's actually going to be different because Stiefel manifold in general has no group structure. So so in some sense, it's a generalization of the prior work. So what is a Stiefel manifold? It's a collection of matrices. Importantly, not necessarily square. Okay, so it's n by m. N is always greater or equal to m. So think about tall matrices. And those matrices have to satisfy an orthogonality constraint to be on the Stiefel manifold. More precisely, you have n by m matrix as an element of this set, and in order to qualify, you have to basically have orthonormal columns. Okay, so each column has to be orthogonal to all the other columns, and also each one has to normalize to each one has to have a 2 norm of 1. That's what really this orthogonal constraint is about. And of course, there's a special case when m is equal to n. You do have a group structure. So this case degenerates to what is known as the orthogonal group. But in general, you don't have any group structure. Why do you care about optimization on Stiefel manifold? For example, okay, let's do a warm-up exercise. Very simple, but actually very important in data sciences and even in traditional sciences and engineering. So it's called the leading eigenvalue problem. So given an n by n matrix A, you want to find the largest m eigenvalues of the matrix. And this is a non-trivial problem if n is very big, say 1 billion, and m is very small, say 10. One way to do it is to actually cast it as an optimization problem. Okay, so you look for basically a collection of orthonormal bases in n dimension, but you only look for m of them. Okay, so they actually form a member of the Stiefel manifold. And then you project this matrix A onto this subspace spanned by those bases. And then you maximize, you compute the sum of eigenvalues of the projection. And of course, that's given one subspace, but because you look for the largest m eigenvalues, you maximize the sum. You look for the subspace that maximizes the sum. Okay, so that's why this can be formulated as an optimization problem, which is nice if m is small, because you're basically not touching the other irrelevant eigenvectors, which are abundant. But of course, you see, also you have to do this Stiefel optimization problem, and you need to do it exactly on the manifold, because you don't want to mess up with the orthonormal basis. Okay, so that's one motivating example. And of course, some people may say, okay, this is nice. It seems pretty general, but it seems also pretty simple because the objective function is a quadratic function of x. Well, one thing that I want to say is that quadratic doesn't mean easy because of the geometric constraint. This is actually a non-convex problem. But if you want harder problem, here you go. So a second example is called projection robust Wasserstein distance. So what is the thing that we try to do here? So we're trying to compute the similarity between two probability measures. So suppose you have two probability measures, mu and nu, and they are actually probability measures on a very high dimensional space. You want to compute the distance between the two measures. Of course, a lot of existing notions are already very powerful. For example, Wasserstein distance. Wasserstein distance is defined as the following. So you consider basically all possible couplings between the probability measures. What does a coupling mean? A coupling is basically a joint distribution such that its x marginal is mu and its y marginal is nu. Okay, so you optimize over all the possible couplings. You look for the best coupling such that you minimize some cost. What is this cost? It's called Earth mover distance. Roughly speaking, okay, so you are trying to move probability mass of x of mu given by x to probability mass of nu given at location y. You try to move those Earths. And of course, you don't want to move too far. You want to minimize the distance of travel. So that's the meaning, roughly speaking, the meaning of this cost function. And then you get Wasserstein distance. It's extremely powerful, but it's also very costly to compute, especially if you have a high dimensional situation. A lot of efforts have been made to do some approximation of this computation, and in particular, a collection of experts proposed one solution which is called projection robust Wasserstein distance. So the idea is the following. So maybe your probability measure or data that represent the probability measures actually have low dimensional structure. And suppose you already know the low dimensional structure. Say you have a low dimensional subspace represented by some orthonormal basis u. And then what you can do is you can compute a Wasserstein distance between projected m-dimensional distributions. Okay, so you project the original n dimension to m dimension. And if m is very small, this is more manageable. But of course, you don't really know what this subspace is. So you have to actually look for it. So you have to do an alter maximization that looks for the best subspace. So this is computationally more manageable. Like I said, if m is much smaller, and also they have shown that this is very robust. For example, okay, so if your data really have low dimensional structures, and then it also has some outliers. After you do this projection and look for the projection, the outliers don't matter. Okay, so this allows you to focus on the essential component of the data, which has arguably low dimensional structure. But you see, okay, this is also a Stiefel optimization problem. And you again need to do this exactly on a manifold. You don't want regularizers. You want to be exact. Otherwise, you mess up the basis. The last example is something that we are very excited about because we sort of invented. So it's about making transformer, which is a very cool machine learning architecture, even better. So in a nutshell, transformer is a recent but extremely powerful machine learning, deep learning architecture. And It was first invented for natural language processing because it basically handles sequences. But now it percolates into other downstream applications such as computer visions. And it basically has an infinite reference window, and that's why it's powerful. It's better than recurrent neural network, which has a short reference window. Things like LSTM, for example, were invented to increase the reference window, but it's still not infinite. But attention mechanism, which transformer uses, actually has an infinite time window. And by the way, I got those nice illustrations from Michael Fai, well, his blog. So I'm very thankful. It's very clear. And transformer actually does this infinite reference window while something called attention layer, or more precisely, multi-headed attention layer. And attention layer basically tries to characterize interactions between words in a sentence, and the interactions can be actually long range. Okay, so it's just like this. And mathematically, what happens is that this attention layer has things called attention heads. Each attention head has trainable parameters, which are weight matrices like this. And even though people are still trying to understand transformer, roughly speaking, those weight matrices characterize interactions between words. And of course, there's no unique way in which words actually interact with each other. So that's why they actually use the multiple attention heads to incorporate different ways in which words actually interact. And of course, you don't know these interactions a priori, so you have to learn them. That's why you have to train. You have to train the model. You have to find those W's from the training data. But then we ask ourselves, okay, so if those W's actually characterize correlations between words, why don't we make it orthogonal? This way, maybe we can make the attention, we are not wasting attention. Maybe we can make the attention mechanism more efficient, more effective. Okay, so we tried this. And if you think about it, there's actually no unique way in which we can impose orthogonality. Way one, you take each head. Each head has this WIQ and WIK. You can require each one of the two matrices to be orthogonal. So you require it to be on the Stiefel manifold. And when you train, you require those trainable variables to stay on the Stiefel manifold. Way two, you can require orthogonality across all heads, which means mathematically you have to concatenate all those weight matrices across all heads, and then you have a bigger matrix, and you require it to stay on a bigger Stiefel manifold. We tried both. We tried both on something very popular called vision transformer, which applies transformer to computer vision, to basically image classifications and more. We trained the model from scratch, and we tested on standard tested data sets such as CFAR 10 and 100. And we found if you require orthogonality within each head, namely way one, you get better performance than orthogonality across heads. But that's still much better performance than if you just do the vanilla version. So training in Euclidean space requiring no orthogonality. In fact, if you just impose a simple orthogonality constraint to the original vanilla version of vision transformer, you can get much better performance than the Euclidean version. And you can even beat later improvements, fancier models, simply just by doing nothing but orthogonality. But there's a catch. The catch is only if you train these models by our optimizers. There are existing optimizers. For example, you can do it very well if you don't incorporate momentum, but you actually get results that may be even worse than the original vision transformer. So our optimizer is actually doing something. But anyway, so that's a very long motivation. So hopefully you are convinced why we want to do this abstract, non-trivial problem of optimization on Stiefel manifold. The rest is how do we do it? So we actually use a variational approach because it's going to be friendly to non-Euclidean spaces, and it naturally introduces a very important notion of momentum. What is momentum? It really originates from mechanics. And of course, you cannot avoid Newton if you want to talk about mechanics. So Newton said, the rate of change in momentum is given by the force. It's very simple, but it's almost half of the explanations of how our world actually operates. So momentum, therefore, is given by basically velocity. So the time derivative of position q times mass. Sorry, I missed the message, and I don't know how to use WebEx.
Yeah. Okay. So if you want to answer that, the shouting asked, how much better is the orthogonal transformer better than vanilla transformer in terms of
yeah. So okay. So great question. So we can improve the prediction error by about 1.5%, and the fancy model improves vanilla vision transformer by about 0.3%. Okay, so 0.3 versus 0.1, we think it's a significant improvement. But there are a lot of technicalities. So I'll try to talk about these momentarily. But that's of course a very important question. Thank you. Okay, so yeah, so therefore this is just a system of ODEs that models Newton's law. But then Lagrange came along. Lagrange, oh, I forgot to mention, sorry. So here, P dot is of course given by the force, and we are considering a conservative situation where F, the objective function, is going to be the potential. So that's why I have the force being given by the negative gradient of the potential. I'll come back to this. And then Lagrange came along. Lagrange said, okay, there is an equivalent variational principle in which you actually first define an action functional S. It's a functional because it's a function of functions. So it's mouthful, but S is a function of actually trajectory. So Q is a trajectory in position space. And this action functional is defined as the integral of Lagrangian evaluated along the trajectory. And if you define the Lagrangian to be kinetic energy minus the potential energy, and then you do the first variation, meaning you look for the critical point of this functional, and then you see the corresponding Euler-Lagrange equation is exactly the same as Newton's equation. Okay, so this is an equivalent but deeper formulation of Newton mechanics. How is it relevant to optimization? So far, there's no relevance because the Lagrangian is actually independent of time explicitly. So there is a time translation symmetry, and therefore there's a conservation law. The total energy of the system, namely kinetic energy plus the potential energy, is a constant. It's independent of time. So if you let the dynamics go, you will see a constant exchange between the kinetic energy and the potential energy. F is never going to be minimized. But that is really because you have time translation symmetry. So if you break the symmetry, if you make L to be time dependent explicitly, then you no longer have conservation of energy. So in a beautiful paper by V.B. Sono, Wilson, and Jordan, they introduced an explicit way, which is to multiply the original Lagrangian by a time-dependent explicit function. And then you can write down the corresponding Euler-Lagrange equation. If you like, you can rewrite it as a first-order system. And P, again, changes according to a net force. But it's no longer just this conservative force. There's additional frictional force due to this time dependence. And this frictional force basically removes the energy from the system. And you can actually prove that as t goes to infinity, the q, the position variable, actually converges to a local minimizer for sure. So that's why this dynamics is actually an optimization dynamics now. And it's closely related to optimization algorithms, in fact, and that's why this paper is a foundational seminal work. I mean, it also has, it's based on previous work as well, but let me skip all the details. So if you choose R such that gamma is 3 over T, you have some ODE. If you choose a particular discretization of the ODE, you actually recover a classical optimization method called Nesterov accelerated gradient for convex functions. If you choose gamma to be a constant, one discretization gives you another optimization method called Nesterov accelerated gradient for strongly convex functions. And if you discretize in a different way, you can recover something called heavy ball, which is also very popular. And all these should be contrasted with gradient descent, which is a forward Euler discretization of gradient flow dynamics. And there, no momentum is being used. And that makes a difference. In fact, let's take NAGC for an example where C stands for convex. Okay, so if F is convex, you can prove that NAGC converges like 1 over k squared, where k is the number of iterations, whereas gradient descent only converges like 1 over k. So that's, you see, this is a much faster convergence. And that's why people say, well, that's one of the reasons that people say momentum gives you acceleration. So that's why we want momentum. We actually want everything for optimization of Riemannian manifold. And this is actually pretty hard. This is very non-trivial. And that's why well, especially if you want to directly work with the ODE or the discrete algorithm, that's very hard. That's why we actually dig deeper. We start with the variational principle. But before I describe how to do it, let me first comment, give you a very quick illustration of why Riemannian optimization is non-trivial. So let's say, suppose you also want to do something similar to before, namely you want to use gradient to do the optimization. So if you know optimization, this is called first order method, first order information of F. And then you should ask yourself, what do you mean by a gradient? For example, so if G is a 2 by 2 orthogonal matrix, so this is a manifold. And let's take a toy example where the objective function is the determinant. And then you may say, oh, well, I'm pretty sure you won't say, but some careless person will say, okay, the determinant is easy to compute, and then you collect all the partial derivatives, and there you go, you form the gradient. That's going to be wrong because orthogonal matrices actually have constant determinant. Okay, so the determinant is either +1 or -1, and it's actually a constant on each connected component of the manifold. So the gradient is actually 0. So what's wrong? The reason is because the manifold is actually one-dimensional. In this case, it's not four-dimensional. A, B, C, D's are not independent. You cannot just do partial derivatives. Okay, so hopefully this shows just the tip of the iceberg of why manifold optimization is a deep field. I'm always very nervous because I'm afraid that I miss important contributions. So let me know if I do. But it's relatively safe to say that if you don't care about momentum, if you just want to do gradient descent on manifold, this is very well studied. What's new here is we have an intrinsic way of adding momentum, and as a consequence, we get an algorithm that is very fast and very accurate. So like I said, the variational principle is a residue. So Euclidean space uses this variational principle. What about manifold? So a pure mathematician would say, oh, that's trivial because, so you still have trajectory. It's just the trajectory is moving on the manifold. And for that reason, by the way, I replace Q by G. It's still a function of time, but it's moving on the manifold. And then G dot is in the tangent space. And if you have a Riemannian manifold, you have an inner product structure in the tangent space. So you can just replace the previous kinetic energy by an inner product in the tangent space. And then you have your Lagrangian, you can do the variational principle. Yes, so in theory, this will work. You will get Euler-Lagrange equation that are still ODEs, which correspond to optimization dynamics. In practice, the ODEs are pretty terrible. They are not very explicit. And if you want to further discretize the ODE in order to get an algorithm, that's going to be a nightmare. So you have to do something smart. In one of our work, we had a solution when G is a group. So when G is a group, you can do something like, you don't want to deal with G dot because it's in a tangent space, which is changing as G moves. So you can pull everything back to something called Lie algebra. And this is done via some fancy, abstract nonsense called reduction via trivialization. Very few people care. I will not talk about it. It's not applicable here because now we care about Stiefel manifold, and Stiefel manifold is not a group. So what do? We do something else. So we have to, we revised the original variational principle. We use something new called a constraint variational principle. So what is the original variational principle? So you have this Lagrangian. You want the first variation of its integral to be 0. So that seems to be very innocent, but in fact, a lot of details are under the rug. The details, what matters is that, okay, so when you do the first variation, you have to vary basically x in a function space. And this function space looks complicated. Okay, x is a function of time. At each time, x is actually on the Stiefel manifold, and x dot is actually on the tangent space. So this function space is highly nonlinear. It's very, very hard to do the first variation. So we do something else. We introduce a function Lagrange multiplier. This lambda is a function of t, and at each time t, it basically tries to enforce this constraint of Stiefel. We add this function Lagrange multiplier to the original Lagrangian, and we do first the variation. Very importantly, in unconstrained flat function space. Okay, so x now is no longer constrained. It's still a function of time, but at each time, it's just n by m matrix. And lambda is n by n matrix. It's a Lagrange multiplier. So you can do this without worrying too much about the geometry. That's still non-trivial because of this additional variable lambda. But we have actually technology to actually compute it out. So this is funny because this technology was developed by us for completely different application in astronomy. But anyway, we can actually get this lambda, and by the end of the day, we can get explicit ODE in Euclidean space without worrying about this lambda at all. So I need to be more concrete by this, and in fact, this Euclidean space is very important. So let me be more concrete. So we can really get explicit ODE for all possible Riemannian metrics, but for concreteness, let's choose a metric tensor, and then the Lagrangian becomes something like this. So you don't really have to worry about the geometry anymore. You just have nonlinearity if you like. And the metric tensor has a parameter A, and it can be anything in our setup. So you may think this is restricted anyway because I specified the metric tensor, but in fact, the literature only considered that A equals to 0 or A equals to a half. So the literature is even more restricted than us. And if you use this metric tensor, you can obtain optimization ODE, which looks like this. It's very complicated. You don't have to stare at it. I'll explain the key details. So x is the variable that you want to optimize. It changes in time. As time progresses, x will become better and better. Q is the momentum, the associated momentum variable. Q changes according to something very complicated. But what matters is, number one, here, what you use is actually the Euclidean derivative. It's basically the bad derivative that I mentioned earlier. But now you don't have to worry about the geometry. You just take all the partial derivatives and plug it in here and also here and here. The dynamics will take care of the geometry for you. And in fact, you don't have to even think about the Stiefel manifold anymore for now, because everything is actually done in Euclidean space. X is just an n by n matrix, and so is Q. But if you evolve this dynamics, it automatically does the geometry for you because X and Q will stay exactly on the manifold. What that means concretely is X has to satisfy this orthogonal constraint for all time. Q has to satisfy this equation, which is basically requiring Q to be in the tangent space. And this dynamics is automatically guaranteed to converge to a local minimum of F. Okay, so depending on your taste, you may think this is great or this is nothing, because this is so far just the imagination of a pure mathematician. It's not an algorithm. So we have to discretize the time of this dynamics to get an optimization algorithm. What we want is, number one, after the time discretization, we have to stay exactly on the manifold, meaning that I have to satisfy the previously two constraints, which is non-trivial. For example, if you use Euler or Runge-Kutta or anything that is off the shelf, it's not going to be working. But moreover, we want the method to be explicit, and in fact, as efficient as possible. For example, X is n by m. N is big, m is small. So we want iteration complexity computational complexity that depends on m as much as possible, but as little on n as possible. Okay, we don't want n. And also, if you know Riemannian optimization, people oftentimes have to do exponential map. Okay, so you take the derivative, you do this exponential map so that you can stay on the manifold. And in our case, the exponential map is just the matrix exponential. We don't want to do it either. People sometimes use something called Cayley transform as an approximation. We don't want to do it either because these things are great, but they are computationally very expensive. We don't want to do these either. This is a highly non-trivial problem. For the sake of time, let me skip all the details, but basically we have methods that can satisfy all those requirements. You can read the paper for details. We can talk also offline. And the method can be extended to adaptive learning rate. So we have an Adam, a Stiefel version for Adam as well. Okay, so that's our method, and we tried it on transformer. So if we, so I guess people are leaving. So how much time I have left?
Yeah, Molei, please don't worry about the time constraints. I mean, it's a recording, so they can come back and then rewatch it. So I mean, okay. Yeah, take your time.
Because I want to have more discussions rather than just me talking. So, okay,
I see.
Let me be brief. So there are clearly a lot of information in this table, but basically remember we have two types of constraints that we proposed. Either we can have orthogonality across all heads, or all heads of the attention, or we can have orthogonality only within each head. So we have two big classes, and in each big class, we have two smaller classes. Either you can do stochastic gradient descent, or you can do Adam, which is adaptive learning rate version. Blue indicates the best within each one of the four subclasses, and underscore means the best across all classes. This green class is the baseline. It's the vanilla vision transformer, and also the last class is improved model, fancier model that improves upon vision transformer. And you see number one. Okay, so if you have orthogonality within each head, you get an error which is like 8.3%, which is better than 8.8% if you have orthogonality across all heads. But even that is still much better than 9.7% error if you don't do any orthogonality constraint. And you see, okay, so you have about 1.4% improvement over the vanilla version, and that's a significant improvement because we have to be in the context. So if you use the later fancier model, for example, this one, you can get 9.5% error. So that's already better than the original one. That's better than the original one by about 3.3%, but we actually get more than 1%. So So we don't have to do anything, just impose orthogonality, and then we can get further improvement. And also important to note is that you get those improvements only if you train by our optimizers. For example, here is a very good method, but it doesn't have momentum. Okay, so if you use this momentum list method, you only get 12.9% error. So it's even worse than the original version. So optimizers do matter a lot. Let me skip the projection robust Wasserstein distance example, as well as the simple leading eigenvalue problem. Okay, let me still say something about this. So remember, this problem is that given an n by n matrix A, you want to find its top m eigenvalues, and it's non-trivial if n is very big and m is small, and that's why we formulate it as an optimization problem. So this is a problem simple enough that we can do a lot of tests. So convergence, for example, our method is the one at the very bottom. It converges the fastest. Manifold preservation, we get manifold preservation up to machine precision. What is interesting are also these two plots. What are they? They are basically validating our theoretical claim about the per iteration computational complexity. So our computational complexity per iteration is n times m squared. And this is better than many existing methods with momentum, which is n squared times m. Okay, so n is much larger than m, so therefore, the above one is much better. The right plot is something that fixes n fixes m and only changes n, and you can see, existing methods has this quadratic growth of computational complexity, computational time with n, but ours has linear growth with n, which is the best you can hope for. And on the left, if you fix the ratio of n over m and you increase either one of them, you see all methods increase cubically. So that's some remark about the computational complexity. But let me summarize. Okay, so we do momentum accelerated optimization on manifold using variational principle. The original one is too complicated, so we have actually some revision, which is constraint variational principle, and with that we can obtain actually optimization dynamics in continuous time on actually Euclidean space. So you don't really have to worry about manifold at this stage, even though the dynamics actually stays exactly on the manifold. And then we have to discretize, and this is where you have to be very, very careful because you want to exactly preserve the manifold, and we managed to do so. And as a consequence, we get very accurate and efficient gradient descent method accelerated by momentum for Stiefel manifold. Some applications include, you can actually make attention mechanism to be suitably orthogonal, and you can get significant improvement of vision transformer. You can also make the notion of a very powerful notion of projection robust Wasserstein distance even better. So I think I should stop here. Thank you so much for your attention and feedback.
Thank you, Molei, for the wonderful talk. There's a one question you haven't answered. It was from the Harsh. He asked, how is adding time-dependent in Lagrangian different from adding a dissipation term via Lagrangian D'Alembert principle?
Oh yeah, thank you. Great question. So you can actually do D'Alembert principle as well. You can add a D'Alembert term to introduce external forcing. But that, roughly speaking, that's not easy to generalize to manifold. So if you introduce a time dependence, that's somehow more intrinsic. It's independent of the coordinate. So that's why it can be used for those manifold generalizations. That's a great question. Thank you.
All right. Any other question? I was impressed by how you used the dynamics to come up with the improving the optimization of the neural network, algorithm that was very nice. In some sense, it was analogical, where the Monte Carlo and there's a Hamiltonian Monte Carlo, and the Hamiltonian Monte Carlo is kind of thought of as a physics-based inspired the Monte Carlo sampling method. So I guess your approach is have the similar
Yeah.
motivation.
Yeah,
there.
yeah, I'm so glad you mentioned this. Because in fact, some of the things that I didn't mention is sampling, and you can have naive Monte Carlo approaches like metropolis hasting. You can also have a Hamiltonian version, which is in some sense adding momentum to accelerate the sampling algorithm, and this is something that we do a lot. So we love this kind of stuff. So I couldn't agree more with you. So in fact, there is something called there's also something called overdamped Langevin, which is a stochastic generalization of gradient flow or gradient descent, if you will. And one can add momentum. One can actually have something called kinetic Langevin, which is like a momentum version. That is closely related to stochastic gradient descent with momentum, etc. And that does accelerated sampling, which is sort of like a probabilistic generalization of optimization. So these are some of the things that we are very fascinated about.
Very nice, very nice.
And
All right, go ahead.
They suit very high dimensional statistical inference problems very well because the momentum can improve the dimension dependence, etc.
Very nice, very nice, very nice. All right, sounds good. Is there any other questions from audience? I don't see any. Well, if that's the case, then let's thank our speaker. I'm sure the people who left early, they can come back and watch, and then probably they can contact you personally, and you guys
Sure,
can have
that'll be a
a
pleasure.
further discussion, and hopefully that will lead to the future collaboration as well, because that's the ultimate goal of this
That'd be
seminar
great.
series.
Yeah.
So
Yeah,
thank you. Let's thank our speaker today, Molei.
Yeah,
Thank you
thank you
so
all.
much.
Thank
You
you all
did
for
a
coming.
wonderful job. Yeah. All right,
Nice
Molei.
talking to you. All right. See
Yeah.
you.
Okay, let me stop.